April 13th, 1970, 9:11 p.m. Houston time. The Mission Operations Control Room on the third floor of Building 30 at the Manned Spacecraft Center, Houston, Texas. Cy Liebergott, 33 years old, sat at the ECOM console in the second row of flight controllers, staring at a telemetry readout that did not make physical sense. Liebergott was the electrical, environmental, and consumables manager for the White Team, the flight control team led by Gene Kranz that had drawn the overnight shift on the 9th day of a lunar mission, so routine that the three major American television networks had declined to broadcast the crew's evening telecast live. 15 minutes earlier, James Lovell, Jack Swigert, and Fred Haise had finished their televised tour of the spacecraft to an American public that, by spring of 1970, had grown bored with men flying to the moon. The numbers on Liebergott's screen had begun behaving strangely approximately 90 seconds earlier. Oxygen tank number 2 pressure was reading anomalously high, then anomalously low. Then it was reading nothing at all. Fuel cell number 1 current was dropping. Fuel cell number 3 current was dropping. Caution and warning lights were illuminating across multiple subsystems in a pattern Liebergott had never seen in 3 years of flight controller training. His first conclusion, the conclusion any experienced controller would have reached in the same position, was that his instrumentation had failed. Spacecraft telemetry sometimes glitched. Multiple simultaneous anomalies across unrelated subsystems was the classical signature of a sensor failure rather than a real spacecraft problem. 205,000 miles above Liebergott's console, beyond the gravitational midpoint between Earth and Moon, Command Module pilot Jack Swigert had pressed a switch on his instrument panel 95 seconds earlier. The switch, designated cryostir, activated small electric fans inside the spacecraft's oxygen and hydrogen tanks. The fans were intended to stir the cryogenic propellants so that quantity measurements could be taken accurately. The procedure was routine. The crew had performed it on every previous Apollo mission without incident. Mission Control had requested it as part of a standard housekeeping checklist before the crew's sleep period. The transmission that arrived at Houston 17 seconds after Liebergott's instruments first began misbehaving consisted of 7 words spoken in the calm, professional cadence of a 38-year-old test pilot who did not yet understand the magnitude of what had just occurred. Jack Swigert's voice came through the speakers of Mission Control at 9:07 and 53 seconds, Houston time. "Houston, we've had a problem here." What Cy Liebergott did not know, what Gene Kranz at his home 12 miles away did not know, what the 3 astronauts trapped inside the wounded spacecraft did not yet fully comprehend, was that the cryogenic oxygen tank that Swigert had stirred 95 seconds earlier had just detonated. The explosion had ripped a 13-foot panel from the side of the service module, severed propellant lines to 2 of the 3 fuel cells, and committed the crew of Apollo 13 to a death sentence that the laws of physics declared non-negotiable. 3 American astronauts were now flying toward the moon in a crippled spacecraft with insufficient oxygen, insufficient electrical power, insufficient water, and insufficient time. Over the next 87 hours, the Mission Operations Control Room in Houston, Texas, would conduct what historians of aerospace engineering now regard as the most extraordinary improvisation in the history of human technology. By the spring of 1970, the American lunar program had become a victim of its own success. Apollo 11, in July of the previous year, had captured the attention of an estimated 600 million people worldwide. Apollo 12, 4 months later, had confirmed that the lunar landing was a repeatable engineering achievement. By the time NASA announced the crew assignments for Apollo 13, in August of 1969, the American public had begun to treat lunar missions the way it treated commercial air travel, as a remarkable technical accomplishment that no longer required active attention. Television ratings for Apollo 12's lunar surface activities had fallen by 60% compared with Apollo 11. Newspaper coverage moved from front pages to interior sections. NBC News had quietly decided in February 1970 that it would not broadcast Apollo 13's mission events live unless something went wrong. The crew assigned to fly the mission represented one of the deepest pools of operational experience in NASA's history. James Arthur Lovell, 42 years old, was the senior crew member and mission commander. A graduate of the United States Naval Academy and a former test pilot at the Naval Air Test Center at Patuxent River, Maryland, Lovell had already logged 572 hours in space across 3 previous missions. He had flown Gemini 7 with Frank Borman in December 1965, setting an endurance record of 14 days in orbit. He had commanded Gemini 12 in November 1966, flying with Buzz Aldrin. He had been the command module pilot of Apollo 8, the Christmas Eve 1968 mission that had become the first to carry human beings around the moon. Apollo 13 would be Lovell's 4th spaceflight, and, he understood when he accepted the assignment, almost certainly his last. At 42, he was old for an astronaut. After Apollo 13, he planned to leave NASA for the private sector. Frederick Wallace Haise, 36 years old, was the Lunar Module pilot. A former Marine Corps fighter pilot and Air Force research test pilot, Haise had been selected as an astronaut in April 1966 and had spent the previous 4 years training without ever flying in space. Apollo 13 would be his first mission. The original command module pilot, scheduled to fly with Lovell and Haise since August 1969, had been Thomas Kenneth Mattingly. 3 days before the scheduled launch on April 11, 1970, NASA flight surgeon Charles Berry made a decision that would prove unintentionally life-saving. The backup lunar module pilot, Charles Duke, had been exposed to German measles during a family visit. Crew immunity testing revealed that Mattingly had no antibodies against the disease and was statistically likely to develop symptoms during the mission. Berry, applying flight rules written years earlier, removed Mattingly from the prime crew. His replacement, hastily promoted from the backup crew, was John Leonard Swigert, a 38-year-old former Air Force pilot with no previous spaceflight experience. The mission objective, decided 18 months earlier by NASA planners, was a lunar landing in the Fra Mauro Highlands, a geologically significant region selected because the dispersed rocky debris in the area was believed to contain samples ejected from deeper lunar layers during the impact that had formed the Imbrium Basin nearly 4 billion years before. From a scientific standpoint, Apollo 13 was potentially the most valuable mission of the program to that date. From a public relations standpoint, it was the moment the American space program had become routine. The Saturn V rocket that lifted Apollo 13 from Launch Complex 39A at 1:13 p.m. Eastern Standard Time on April 11, 1970, carried a crew that the American television networks had largely decided was no longer worth their continuous attention. The true antagonist of the Apollo 13 story was not the cold equations of orbital mechanics, nor the unforgiving distance between Earth and Moon. It was an oxygen tank, designated by serial number 100024XTA0008, that had begun its existence as an unremarkable piece of standard Apollo hardware and had ended its existence as the most dangerous component ever flown on an American spacecraft. The tank's history, reconstructed in painstaking detail by the Cortright Commission in the months following the mission, would reveal that Apollo 13 had been launched with a bomb in its belly. Nobody at NASA had recognized the bomb. The procedures that should have detected it had failed. The engineers who had handled it had assumed it was safe. For 56 hours of flight, the bomb had waited in silence, suspended in 320 pounds of liquid oxygen pressurized to 900 pounds per square inch, until Jack Swigert's finger pressed the cryo stir switch. The tank had been manufactured by the Beech Aircraft Corporation in 1966 to specifications issued by North American Rockwell, the prime contractor for the Apollo Command and Service Module. It had originally been installed aboard the Apollo 10 spacecraft in 1968, intended to fly the dress rehearsal mission for the lunar landing. During a routine maintenance procedure at the Kennedy Space Center in October 1968, the oxygen shelf to which the tank was mounted had been removed for modification. A technician had failed to remove all 4 retaining bolts before attempting to lift the shelf. The shelf, with the tank still attached, had dropped approximately 2 inches before being caught. The incident was logged. The tank was inspected. No visible damage was found. The tank was certified for continued use. What the inspection had failed to detect, and what no inspection procedure available to NASA in 1968 could have detected, was that the 2-inch drop had loosened a fill tube assembly inside the tank. The displacement was microscopic, perhaps a few thousandths of an inch, far below the threshold of any non-destructive testing technique then available. The tank functioned normally in all subsequent ground tests. It was eventually removed from the Apollo 10 spacecraft, refurbished, and reinstalled in the Apollo 13 service module in November 1969. By the time it was loaded with liquid oxygen for the first time in March 1970, the tank had been examined, signed off, and approved by no fewer than 7 separate NASA quality assurance inspectors. None of them knew about the loosened fill tube. None of them could have known. The fatal sequence of events began on March 27, 1970, 15 days before the scheduled launch. NASA technicians at the Cape conducted a routine pre-flight detank test in which the cryogenic oxygen was emptied from the spacecraft tanks to verify proper drainage. Tank number 1 drained normally. Tank number 2, the tank that would eventually kill itself, did not. The loosened fill tube prevented the standard detank procedure from removing the residual oxygen. Approximately 92% of the oxygen remained inside the tank with no way to expel it through normal means. The engineers at the launch site faced an awkward decision. The standard procedure for an undrained tank was to remove it from the spacecraft, return it to the manufacturer for inspection, and install a replacement. This would have delayed the Apollo 13 launch by at least 4 weeks. The launch schedule, driven by lunar lighting requirements at the Fra Mauro landing site, did not easily accommodate a 4-week delay. A senior engineer proposed an alternative. The tank contained internal electrical heaters designed to maintain the oxygen at usable temperatures during long-duration flight. These heaters could be activated to boil off the trapped oxygen. The procedure was unconventional but not unprecedented. The heaters were rated for continuous operation. The trapped oxygen would evaporate harmlessly into the atmosphere. What the engineers proposing this solution did not know, what was not documented in any technical manual they consulted, was that the thermostats inside the tank had been designed in 1962 to specifications calling for 28-volt direct current power, the standard electrical system specification for early Apollo hardware. In 1965, NASA had upgraded the spacecraft electrical system at the Kennedy Space Center to 65 volts to accommodate increased power demands. Most spacecraft components had been redesigned to handle the higher voltage. The oxygen tank thermostats had not been. The redesign requirement had been overlooked in a document review process that the Cortright Commission would later describe as institutional failure, spanning 4 separate contractor organizations. On March 27, 1970, NASA technicians applied 65 volts of direct current to thermostats designed for 28 volts. The thermostats, designed to open and disconnect the heaters when internal tank temperatures exceeded 80 degrees Fahrenheit, instead welded themselves closed. The heaters continued to operate. Internal tank temperatures, monitored by external instrumentation that read maximum allowable values rather than actual values, were later estimated to have reached 1,000 degrees Fahrenheit. At this temperature, The Teflon insulation surrounding the electrical wiring inside the tank melted, exposing bare copper conductors. The detank operation continued for approximately 8 hours. By the time it concluded, oxygen tank number 2 had been transformed into an electrical short waiting to happen, immersed in pure liquid oxygen, with stripped wires lying against the tank wall. Nobody knew. The tank was certified flight-ready. On April 11, 1970, it was launched toward the moon. At 55 hours, 53 minutes, and 20 seconds of mission elapsed time, the Apollo 13 spacecraft was 205,000 miles from Earth, traveling at 3,301 feet per second along its translunar trajectory. The crew had just completed a 49-minute television broadcast to a largely indifferent American public. Lovell had given a tour of the spacecraft. Haise had demonstrated weightlessness. Swigert, the newcomer, had spoken briefly about his impressions of his first spaceflight. When the broadcast ended at 8:59 p.m. Houston time, the crew began stowing the television equipment and preparing for the evening rest period. In the Mission Operations Control Room 300,000 feet below them, the White Team flight controllers were running through the standard pre-sleep checklist that had been performed without incident on every previous Apollo mission. At 9:06 and 10 seconds Houston time, capsule communicator Jack Lausma transmitted the routine instruction that flight planners had inserted into the checklist 18 months earlier. 13, we've got one more item for you when you get a chance. We'd like you to stir up your cryo tanks. Swigert, floating at the command module pilot station on the right side of the spacecraft, acknowledged the request. He reached forward to the cryogenic systems panel, located on Bay 3 of the main instrument display, flipped 4 switches to activate the stirring fans in the 4 cryogenic tanks, and waited the standard 16 seconds for the procedure to complete. The stirring fans inside oxygen tank number 2 activated at 9:07 and 4 seconds. The bare electrical wires that had been waiting since March 27th, lying against the inside wall of the tank, surrounded by pure liquid oxygen at 900 pounds per square inch of pressure, completed their inevitable electrical circuit. An arc formed between the exposed conductors. In an atmosphere of ambient air, an electrical arc of this magnitude would have produced a brief blue flash and perhaps a wisp of smoke. In an atmosphere of pure pressurized oxygen, with combustible Teflon insulation feeding the reaction, the arc became a fire. The fire became an explosion. The explosion propagated through the tank at the speed of chemical detonation. At 9:07 and 49 seconds Houston time, sensors aboard the spacecraft registered an impact event. The pressure inside oxygen tank number 2, which had been reading 912 pounds per square inch, spiked to 1,008 pounds. The pressure relief valve opened. Then the tank ruptured. The detonation tore open the dome of the tank, ejected the tank's contents into the surrounding service module bay at supersonic velocity, and overpressurized the bay until the external panel covering Bay 4 blew outward into space. The 13-foot panel separated from the spacecraft at approximately 20 feet per second, taking with it portions of the high-gain antenna assembly and inducing a violent rotational motion in the entire spacecraft. Inside the command module Odyssey, Jim Lovell felt the spacecraft shudder. His first thought, recorded in his 1994 memoir, Lost Moon, was that Fred Haise had triggered a sudden cabin repress valve as a practical joke. Haise had used the valve to startle his crewmates twice during the mission, producing a loud bang that traveled through the spacecraft structure. Lovell turned toward Haise's station, prepared to deliver a rebuke. He saw Haise's face. Haise was staring at Lovell with an expression that contained no humor whatsoever. The bang they had just heard had not come from Haise. The master alarm illuminated on Lovell's instrument panel. The caution and warning system activated. 11 separate yellow warning lights illuminated simultaneously across the main display console. The spacecraft attitude began to drift outside its programmed orientation. Lovell glanced at the 8-ball attitude indicator and watched it rotate visibly, an indication that the spacecraft was tumbling. He grabbed the hand controller and attempted to stabilize the vehicle. The reaction control system thrusters fired in response to his inputs, but the spacecraft continued to drift, as if something was pushing it from outside. Lovell could not yet see what was pushing it. The 13-foot section of paneling that had blown into space was now venting a continuous stream of liquid oxygen and structural debris into the vacuum behind the spacecraft, acting as a crude rocket motor that no manual input could fully counteract. At 9:07 and 53 seconds, 4 seconds after the master alarm illuminated, Jack Swigert pressed the push-to-talk button on his communications headset and spoke the words that would become the most quoted phrase in the history of human spaceflight. His voice carried no panic, it carried no urgency. It carried the calm, professional cadence of a test pilot who had been trained to communicate clearly under stress and who did not yet understand the magnitude of what had occurred behind the bulkhead 7 feet from where he was floating. "Houston, we've had a problem here." The transmission reached mission control 1.3 seconds later. Capsule communicator Jack Lousma, sitting at his console next to Flight Director Glenn Lunny, leaned toward his microphone and replied with 5 words that would also enter the historical record. "This is Houston. Say again, please." Eugene Francis Kranz, 36 years old, was at his home in El Lago, Texas, 12 miles south of the Manned Spacecraft Center, when his telephone rang at 9:11 p.m. on the evening of April 13, 1970. Kranz had served as flight director for the lunar landing of Apollo 11 9 months earlier and had been assigned to lead the white team for Apollo 13. His shift was scheduled to begin at midnight. The call came from the backup flight director on duty, who informed Kranz that something had occurred aboard the spacecraft that the black team flight director, Glenn Lunny, did not yet understand. Kranz reached for the white vest his wife Marta had sewn for him 3 years earlier, a vest he wore for every mission and which had become his trademark, and drove to the Space Center at speeds that would later require a written explanation to the local police. By the time Kranz arrived at the Mission Operations Control Room at 9:28 p.m., the situation had clarified itself in ways that no one in the building wanted to acknowledge. The spacecraft was not experiencing instrumentation failures, as Cy Liebergott had initially hypothesized. The instrumentation was reading correctly. Oxygen tank number 2 was empty. The pressure in oxygen tank number 1 was dropping at a rate that placed it on a trajectory towards 0 within 1 hour and 54 minutes. Fuel cell number 1 had died. Fuel cell number 3 had died. Fuel cell number 2 was producing electrical output at approximately 1/3 of normal capacity and was declining. The command module Odyssey was bleeding its life support resources into space at a rate that could not be stopped because the source of the leak was outside the pressure vessel and therefore inaccessible to the crew. Kranz took his seat at the flight director's console at 9:31 p.m., relieved Lunny from active control of the mission, and began conducting the polling protocol that NASA flight controllers had been trained to execute during emergencies. He addressed each controller in sequence by their position designation and required a direct verbal status report. EECON Liebergott reported the cryogenic systems were failing. GNC Buck Willoughby reported that the spacecraft attitude could not be stabilized using the service module reaction control system. Telmu Bob Heselmeyer, the controller responsible for the Lunar Module systems, reported that the Lunar Module was nominal but had not yet been activated for any flight purpose. Within 20 minutes of taking his seat, Kranz had assembled an accurate picture of his situation. He had 3 astronauts in the dying spacecraft, 205,000 miles from Earth, with a command module that could not sustain them for more than approximately 2 hours, and a lunar module that had been designed to support 2 astronauts for 45 hours, and would now be required to support 3 astronauts for at least 90 hours. The famous quotation attributed to Kranz from that night, the phrase, "failure is not an option," was not actually spoken by him during the mission. The phrase was invented by screenwriters for the 1995 Ron Howard film and would later become the title of Kranz's own memoir, published in the year 2000. What Kranz actually said to his flight controllers at approximately 9:45 p.m., according to the recollections of multiple men who were present, was directed at the room as a whole and constituted an instruction rather than a slogan. "Okay, listen up. When you leave this room, you must leave believing that this crew is coming home. I don't give a damn what the odds are. I don't give a damn that we've never done anything like this before. Flight controllers, from this moment on, are working one problem. We're going to get these men home. You got it?" The decision that committed the rescue effort took form in the next 20 minutes as Kranz and his controllers worked through the available options. The command module Odyssey contained reentry batteries with approximately 45 amp-hours of reserve capacity, intended for the brief period after the service module would normally be jettisoned before atmospheric entry. If those batteries were consumed in flight, the crew would survive the trip back to Earth, but would burn up in the atmosphere during re-entry, because the spacecraft would have no electrical power to operate guidance computers, control re-entry attitude, or deploy parachutes. The re-entry batteries were therefore non-negotiable. They had to be preserved. The lunar module Aquarius, mated to the command module by a docking tunnel, was a fully functional spacecraft in its own right. It had its own electrical power, its own oxygen supply, its own water, its own propulsion system, and its own guidance computer. It had been designed and built to land 2 astronauts on the lunar surface, sustain them for 33 hours, and return them to lunar orbit. It had never been considered as a lifeboat. The concept of using it as one had been mentioned in a single technical paper written in 1965 and had appeared in no flight rules, no contingency procedures, and no simulator training. Kranz polled his controllers. Was the Aquarius capable of keeping 3 men alive for 90 hours? The answer, qualified by significant technical uncertainty, was that it might be. At 9:57 p.m. Houston time, Kranz authorized the transfer. The transfer of the Apollo 13 crew from the dying command module Odyssey to the lunar module Aquarius began at 10:04 p.m. Houston time, 57 minutes after the explosion. The procedure was conducted under conditions that no NASA training program had ever contemplated. The standard powering up sequence for the lunar module required approximately 2 hours of methodical checklist execution performed by 2 astronauts working in the lunar module cabin, while the 3rd astronaut monitored systems in the command module. In normal operations, the procedure occurred in lunar orbit, with both spacecraft fully functional and mission control providing leisurely guidance from Earth. On the night of April 13th, the Aquarius had to be brought to operational status in approximately 15 minutes, with the command module dying around the crew as they worked. Fred Haise floated headfirst through the docking tunnel into the Aquarius at 10:06 p.m. and began activating systems in the sequence that mission control was transmitting from Houston in real time. The lunar module guidance computer required initialization. The cabin pressurization had to be verified. The cooling systems had to be brought online. The reaction control system thrusters had to be enabled. Each step was a procedure that, in normal training, the crew would have rehearsed dozens of times. The procedures Haise was now executing had been rewritten by Mission Control in the previous 20 minutes to account for the fact that the Aquarius was being activated while still attached to a wounded command module in deep space, with no possibility of returning to lunar orbit or aborting the mission. By 10:22 p.m., 16 minutes after he had entered the lunar module, Haise reported that the Aquarius was alive. The next problem facing Mission Control was simultaneously simpler and more terrifying. The command module Odyssey had to be powered down completely. Every electrical system, every instrument, every light, every fan, every heater had to be switched off in a specific sequence to preserve the 45 amp-hours of battery capacity that the crew would require to survive re-entry. The procedure had to be executed perfectly. A single mistake in the shutdown sequence could damage equipment that would later be needed during reentry, and any equipment damaged at this stage could not be repaired before the crew returned to Earth. The man responsible for designing the shutdown procedure in real time, with the lives of 3 astronauts depending on his accuracy, was John W. Aaron, 27 years old, an EECOM specialist who had joined NASA 8 years earlier as a flight controller trainee. Aaron had become legendary inside Mission Control 9 months earlier for his calm direction during the launch of Apollo 12, when a lightning strike 36 seconds after liftoff had temporarily disabled the spacecraft's electrical systems. Aaron, watching the telemetry, had transmitted 4 words that had saved the mission. SCE to AUX. The setting change he had recommended had rebooted the signal conditioning equipment and restored the data stream. Apollo 12 had reached the moon. Aaron had become known among the astronauts as the steely-eyed missile man, the highest informal honor a flight controller could receive. On the night of April 13th, Aaron was assigned to lead a small group of controllers that had not yet been given a name. They would later be called the Tiger Team, after the informal designation that had been used for similar improvised problem-solving groups during earlier missions. The Tiger Team's task was to write from scratch a procedure for powering up the command module from a cold, dead state using only the re-entry batteries as a power source. No such procedure had ever existed. Apollo spacecraft had never been powered down completely during flight and then powered back up. The condensation that would accumulate on the cabin walls during 4 days of cold soak could short-circuit electrical systems during the power-up. The guidance computer, once depowered, would require a complete realignment based on star sightings. The estimated minimum power required for a successful re-entry sequence, calculated by Aaron and verified by his team, was 20 amp-hours, exactly 45% of the available battery capacity. There was no margin for error. Aaron requested authorization to bring in additional resources. The resource he wanted most urgently was Thomas Kenneth Mattingly, the astronaut who had been removed from the prime crew 3 days before launch because of his exposure to German measles. Mattingly knew the command module Odyssey better than any other person on Earth. He had trained in it for 18 months. He had been scheduled to fly it. He had been watching the mission from his home in Houston when the explosion occurred, and had driven to the Space Center within an hour. Aaron and Mattingly entered Building 5, the simulator facility, at 1:12 a.m. on April 14th, 4 hours after the explosion. They did not leave the building for the next 96 hours. By the morning of April 14th, 1970, approximately 14 hours after the explosion, the Apollo 13 crew had stabilized into a routine that would govern the next 3 days of their existence. The command module Odyssey was powered down and cold. The Lunar Module Aquarius was operating on minimal power settings, sustaining the 3 astronauts on systems designed to support 2 men for less than half this duration. Lovell and Haise occupied the Lunar Module cabin. Swigert moved between the Aquarius and the dark, freezing Odyssey, where he was attempting to sleep on the equipment bay floor. The cabin temperature in the Odyssey had dropped to 38 degrees Fahrenheit and was continuing to decline. The temperature in the Aquarius was holding at 55 degrees, but was beginning to fall as electrical systems that produced incidental waste heat were progressively shut down to conserve battery power. The crisis that emerged 12 hours into the lifeboat phase was not one that Mission Control had anticipated, although in retrospect it should have been obvious. The lithium hydroxide canisters aboard the Lunar Module had been designed to remove carbon dioxide produced by the metabolic activity of 2 astronauts breathing for approximately 45 hours of mission time. They were now being asked to remove carbon dioxide produced by 3 astronauts for an estimated 87 hours. The mathematics of the situation were straightforward and lethal. The Aquarius canisters would saturate at approximately the 40-hour mark of the lifeboat phase. Beyond that point, the carbon dioxide concentration in the cabin atmosphere would begin to rise. The threshold of toxicity for carbon dioxide in a closed atmospheric system, established by medical research in the 1950s, occurred at a partial pressure of 7.6 millimeters of mercury. At 15 millimeters of mercury, astronauts would experience confusion, severe headaches, and loss of fine motor control. At 20 millimeters, they would lose consciousness. Above 25 millimeters, they would die. At 7 a.m. Houston time on April 14th, the partial pressure of carbon dioxide in the Aquarius cabin was reading 2.1 millimeters and rising at a rate that placed it on a trajectory to exceed the toxic threshold by the following evening. The command module Odyssey contained spare lithium hydroxide canisters in adequate quantity to solve the problem. The canisters had been designed by the prime contractor for the command module, North American Rockwell, to fit into the Odyssey's environmental control system. They were rectangular. They measured approximately 7 inches by 7 inches at the cross-section. The lithium hydroxide canister receptacles in the Lunar Module Aquarius had been designed by the Grumman Aircraft Engineering Corporation, a separate contractor responsible for an entirely separate spacecraft. They were cylindrical. They measured approximately 5.5 inches in diameter. The two contractors had never been instructed to standardize their canister geometries because no NASA mission planner had ever envisioned a scenario in which canisters from one spacecraft would need to be installed in the other. Edward I. Smylie, the Crew Systems Division Chief at the Manned Spacecraft Center, was assigned the problem at 8:05 a.m. on April 14th. Smylie was 43 years old, a former Navy officer who had been working at NASA since 1962. His division was responsible for the design and qualification of every piece of equipment that came into contact with an astronaut's body, including spacesuits, food packaging, and atmospheric control systems. Smylie understood within minutes of receiving the problem that he was being asked to design, fabricate, and verify the function of an interface adapter using only materials currently aboard the Apollo 13 spacecraft, with no opportunity for ground testing in a time window of less than 6 hours. The inventory of materials available to Smylie's team consisted of items that had been packed aboard the spacecraft for entirely unrelated purposes. Plastic covers from the flight plan manuals, duct tape, which NASA had begun packing aboard spacecraft after the Apollo 7 mission at the suggestion of astronaut Walter Schirra, cardboard from a hatch insulation panel, a spare suit hose from one of the lunar surface spacesuits that would never now be used, one of the astronauts' tube socks. By 11 a.m. on April 14th, Smylie's team had constructed a working prototype of an adapter that allowed command module lithium hydroxide canisters to be installed inside the Lunar Module's environmental control system. The device was approximately the size of a small box and would be referred to within mission control by the nickname mailbox. The instructions for assembling the mailbox aboard the spacecraft were transmitted to the crew by capsule communicator Joe Kerwin, beginning at 3 p.m. Houston time. Kerwin read the assembly procedure aloud, step by step, for 63 consecutive minutes. At 4:18 p.m., Lovell reported that the mailbox was installed. By 5 p.m., the carbon dioxide reading in the Aquarius cabin had begun to drop. At 12:21 a.m. Greenwich Mean Time on April 15, 1970, 76 hours and 33 minutes after lifting off from the Kennedy Space Center, the Apollo 13 spacecraft passed behind the eastern limb of the Moon and entered the radio communications blackout zone that occurred during every lunar mission. The blackout, caused by the Moon's bulk physically blocking line-of-sight transmissions between the spacecraft and Earth-based tracking stations, would last approximately 25 minutes. For mission control in Houston, the blackout produced a particular silence that veterans of the Apollo program would later describe as the heaviest moments they had ever experienced. There was nothing to do during a blackout except wait and watch the mission elapsed time clock advance toward the predicted reacquisition of signal. On April 15th, the silence was loaded with the recognition that the spacecraft inside it was wounded. The crew was dying by inches, and no transmission from Houston could reach them for the next 1,500 seconds. Inside the Lunar Module Aquarius, Jim Lovell drifted at the commander's station with nothing operationally required of him for the duration of the blackout. The free return trajectory that Apollo 13 had been placed on after the explosion was carrying the spacecraft around the moon along a passive ballistic path. No engine burns were required during the lunar pass itself. Lovell had been awake for 38 consecutive hours. He had lost 10 pounds of body weight to dehydration. The cabin temperature had dropped to 42 degrees Fahrenheit, cold enough that Lovell could see his breath condensing in the air in front of his face. He floated at the Aquarius window on the commander's side of the cabin and looked outward. What Jim Lovell saw through that window during the 25 minutes of communications blackout placed him in a position that no human being had ever occupied before. He was looking at the far side of the moon. He was the 18th person to see the lunar far side directly, after the crews of Apollo 8, Apollo 10, Apollo 11, and Apollo 12. But Lovell was the first human being ever to look at the lunar far side, knowing that he was almost certainly not going to return to Earth. Frank Borman, his commander on Apollo 8, had looked at the far side as an explorer. Lovell, 15 months later, looked at it as a man who had begun to compose internal goodbyes to his wife Marilyn and his 4 children. In his 1994 memoir, Lost Moon, co-written with the journalist Jeffrey Kluger, Lovell would describe the moment in language that those who knew him personally would later say captured the dimensions of his character. I looked out the window and saw the far side of the moon passing below me, a place I had never seen and would never see again. Then I rotated my position and looked through the opposite window, and I saw the Earth, a tiny blue and white marble suspended in the blackness. I could cover the Earth with my thumb if I held my hand at arm's length. Everything I had ever loved, everyone I had ever known, my wife, my children, my parents, every friend, every memory, every regret, was contained inside the small blue circle that I could hide behind my thumb. I had flown farther from that blue circle than any human being had ever flown. I was at that moment 248,000 miles from home, and I was not certain that I was ever going to see it up close again. The maximum distance from Earth that Apollo 13 reached during the lunar pass was 248,655 miles, achieved at 0 hours and 21 minutes Greenwich Mean Time on April 15, 1970. This figure constituted, and continues to constitute, the maximum distance from Earth that human beings have ever traveled. In the more than 56 years that have elapsed since April 15, 1970, no human spacecraft has carried a crew farther from the Earth's surface than Apollo 13 carried Lovell, Swigert, and Haise during the 25 minutes of their lunar farside pass. The record holds because no nation has attempted to fly human beings beyond the lunar vicinity since the conclusion of the Apollo program in December 1972. The men who hold this record are, with respect to humanity's exploration of the solar system, the species ambassadors to a region of space that no one else has ever reached. At 12:46 a.m. Greenwich Mean Time, the Apollo 13 spacecraft emerged from the western limb of the moon and re-established line-of-sight radio contact with the tracking station at Goldstone, California. Mission Control received the carrier signal 4 seconds before the first voice transmission arrived. The 4-second interval was sufficient for Gene Kranz, sitting at his Flight Director console 240,000 miles from the spacecraft, to lean back in his chair, close his eyes briefly, and prepare for the next phase of an operation that had not yet entered its most dangerous hours. The maneuver that committed Apollo 13 to its return trajectory was executed at 2:40 p.m. Greenwich Mean Time on April 15, 1970, 2 hours after the spacecraft had passed perihelion at the far side of the Moon. The burn, designated PC+2 and lasting 4 minutes and 23 seconds, fired the descent engine of the Lunar Module Aquarius to accelerate the joined spacecraft along a trajectory that would shorten the return to Earth from the original 87-hour profile to approximately 63 hours. The decision to execute the burn at PC+2, rather than at an earlier or later point, had been made by Mission Control after extensive consultation with the Massachusetts Institute of Technology Instrumentation Laboratory and the trajectory specialists at the Mission Planning and Analysis Division. The burn required Lovell to manually align the spacecraft using the position of the Earth's terminator as a visual reference through the Aquarius window, because the Lunar Module guidance computer had been powered down to conserve electrical capacity. The acceptable error margin for the alignment was less than 1 degree. Lovell achieved the alignment within 1/10 of a degree. The burn was perfect. What remained after the PC+2 burn was time. 63 hours of time, during which the spacecraft would coast along its corrected trajectory back toward Earth, with no further engine burns planned until the small mid-course corrections that would refine the entry corridor in the final 24 hours. The crew had nothing operational to do during this period except survive. Surviving turned out to be more difficult than Mission Control had anticipated. The cabin temperature inside the Aquarius and the connected Odyssey continued to drop as the spacecraft moved further from the sun's direct radiation, and as the powered-down systems ceased producing incidental waste heat. By the morning of April 16th, the temperature in the Odyssey had fallen to 34 degrees Fahrenheit. The temperature in the Aquarius cabin was holding at approximately 38 degrees. Water droplets had begun condensing on the cold metal walls of both spacecraft, accumulating into visible films that ran down the bulkheads and pooled in the equipment bays. Lovell, attempting to sleep in the Odyssey on a temporary basis to give Haise and Swigert more room in the Aquarius, described the experience in his memoir as resembling an attempt to sleep inside a refrigerator that was being used as a humidifier. The water rationing decisions made by Mission Control on April 14th had produced consequences that began to manifest physiologically by the 3rd day of the lifeboat phase. The Lunar Module's water supply, intended to support 2 astronauts during a 45-hour lunar excursion, had to be stretched to support 3 astronauts for nearly twice that duration. The flight surgeons in Mission Control, working with Dr. Charles Berry, had calculated that each crewman could receive 6 ounces of water per day without inducing acute dehydration that would compromise their ability to function during the high-stress reentry phase. This represented approximately 1/5 of the daily water intake that astronauts received during normal Apollo missions. The food packages aboard the spacecraft were almost entirely useless because they required reconstitution with hot water, and the Lunar Module's water heater had been switched off to conserve electrical power. The crew subsisted primarily on dry food and small portions of cold, rehydrated meals. By the morning of April 16th, all 3 astronauts were exhibiting clinical symptoms of dehydration. Fred Haise had developed an additional medical problem that the flight surgeons had not anticipated. The combination of low water intake, cold, and physical stress had triggered a urinary tract infection. By the afternoon of April 16th, Haise was running a temperature of 104 degrees Fahrenheit. He was shivering violently inside his flight coveralls. Mission Control debated whether to inform the crew of the seriousness of Haise's condition and decided against it. Lovell, observing Haise from across the Aquarius cabin, recognized the situation independently and began compensating for Haise's reduced operational capacity without discussing it with his crewmate. In Houston, the Tiger team, led by John Aaron and Ken Mattingly, entered their 4th consecutive day of work in the simulator without sleep. Aaron had taken his last meal at approximately 10 p.m. on April 13th, before the explosion. By April 16th, he had consumed only coffee and a small quantity of food brought to him by his wife, who had driven to the Space Center each evening with sandwiches. Mattingly, who had been assigned to verify each step of the powering up procedure Aaron was writing, had not left Building 5 at all. He slept in 2-hour increments on a cot in the simulator support room. The procedure they were constructing, when completed, would total 39 pages of step-by-step instructions covering the sequence required to bring the command module Odyssey back from its frozen, depowered state into a configuration capable of supporting atmospheric entry. Aaron and Mattingly understood that any error in those 39 pages, however small, would result in the deaths of 3 astronauts within sight of home. At 2:15 a.m. Greenwich Mean Time on April 17, 1970, 6 hours before the planned atmospheric entry, the procedure to reactivate the command module Odyssey began. John Aaron and Ken Mattingly, who had not slept in any meaningful sense for 96 hours, had completed the final version of the powering up checklist at 11:30 p.m. the previous evening. The procedure had been verified in the Building 5 simulator by Mattingly himself, who had walked through every step in the exact sequence in which it would now be executed 200,000 miles away. The 39-page document had passed through review by every relevant engineering specialty within the Manned Spacecraft Center. It had been approved by Gene Kranz at 1:50 a.m. The procedure was ready. The men who had written it understood that no procedure of comparable complexity and consequence had ever been executed on an American spacecraft. Mattingly took his seat at the capsule communicator console at 1:58 a.m. The decision to assign Mattingly as the Capcom for the powering up sequence had been made by Kranz personally. Mattingly knew the command module better than any other man on Earth. He had been scheduled to fly it. He had spent 18 months training in it. If anyone could guide Swigert through the reactivation of systems that had been cold-soaked for 4 days in deep space, Mattingly could. He keyed his microphone at 2:15 a.m. and began reading the procedure aloud. The fundamental danger of the powering up sequence was electrical condensation. The cabin walls of the Odyssey, which had been depowered and exposed to space temperatures for 95 hours, were coated with films of liquid water that had condensed from the cabin atmosphere during the cold soak period. Behind the equipment panels, behind the wiring harnesses, inside the relay boxes and the circuit breaker assemblies, the same condensation had accumulated. Apollo spacecraft had been designed with extensive electrical insulation, but no Apollo command module had ever been powered back up from a fully cold state. The probability of electrical arcing across condensation-bridged conductors during the power-up sequence was not 0. The consequences of an arc in any critical system would be the loss of the spacecraft. Swigert executed the procedure step by step under Mattingly's verbal direction. The capsule communicator transmission protocol, used by Mattingly during the next 2 hours and 17 minutes, would be preserved by NASA in its training archives, and would later be studied in graduate engineering programs at universities, including the Massachusetts Institute of Technology and Stanford. Mattingly's voice carried no urgency, no audible emotion, no detectable signal of the 96 hours of accumulated fatigue. He read each instruction at a measured pace. He waited for Swigert's confirmation. He addressed each potential problem before it could become a real one. When Swigert reported anomalies, Mattingly diagnosed them within seconds and provided revised instructions. The procedure consumed every minute available in the planned timeline and produced no failures of any system. At 6:05 a.m. Greenwich Mean Time on April 17th, with the entry interface approximately 3 hours away, the time arrived for the separation of the service module from the command module. This event, which occurred during every Apollo mission, served to discard the propulsion and life support systems that were no longer needed for the final atmospheric entry. Under normal mission conditions, the service module was jettisoned approximately 15 minutes before atmospheric entry. The Apollo 13 crew had been directed to perform the separation more than 2 hours earlier than the standard procedure, because Mission Control wanted to obtain visual confirmation of the damage that had been done by the oxygen tank explosion. The damage report would be used in the post-mission engineering analysis. It would also be the first time any human being would see what had actually happened to the spacecraft on the night of April 13th. Lovell observed the separating service module through the rendezvous window of the command module Odyssey as the discarded section tumbled slowly away. His transmission to Mission Control at 6:14 a.m. Greenwich Mean Time would be preserved as one of the most vivid descriptions ever delivered by an astronaut in flight. And there's one whole side of that spacecraft missing. Right by the high-gain antenna, the whole panel is blown out, almost from the base to the engine. It's really a mess. Haise, drifting to the window to confirm the observation, photographed the damaged service module with the Hasselblad camera that had been intended to document the lunar surface. The photograph that resulted, designated AS-13 62-8938 in NASA archives, would become the most reproduced image of the Apollo 13 mission. It showed an immense, ragged opening along the entire flank of the service module, exposing internal tankage and structural members that had been violently displaced. Boris Chertok, monitoring the radio intercepts from Moscow, recorded in his diary an observation that he would later expand in his memoirs. What we are witnessing during these days is no longer a space mission. It is a demonstration of what American industrial civilization can accomplish when it focuses its full capacity on saving 3 of its citizens. We have nothing comparable. We would not be able to do this. At 17:53 and 45 seconds Greenwich Mean Time, on April 17, 1970, the command module Odyssey encountered the upper boundary of the Earth's atmosphere at an altitude of 400,000 feet, traveling at a velocity of 24,689 miles per hour. The spacecraft entered the atmosphere at an angle of 6.3 degrees below the local horizontal, the steepest permissible entry angle within the corridor that the trajectory specialists had calculated. Any shallower, and the command module would skip off the upper atmosphere into a return orbit that would carry the crew beyond rescue. Any steeper, and the thermal load on the spacecraft's ablative heat shield would exceed the structural tolerance of the bonded laminate, with catastrophic results. The corridor in which Apollo 13 had to thread the spacecraft measured approximately 2 degrees of arc, and the trajectory team had placed the spacecraft within 1/10 of a degree of the corridor's center. The communications blackout that occurred during every Apollo atmospheric entry was caused by a sheath of ionized air that formed around the spacecraft as compression heating converted atmospheric molecules into plasma. The plasma was electrically opaque to radio frequencies and prevented all transmissions in either direction between the spacecraft and Mission Control. For previous Apollo missions, the blackout duration had been precisely predictable based on the entry profile. Apollo 11's blackout had lasted 3 minutes and 4 seconds. Apollo 12's had lasted 3 minutes and 17 seconds. Apollo 13, entering steeper and faster than any previous mission, was predicted to experience a blackout of approximately 3 minutes and 10 seconds. The blackout for Apollo 13 began on schedule at 17:53 and 45 seconds, when the spacecraft's carrier signal disappeared from the receivers at the Honeysuckle Creek tracking station in Australia. Inside Mission Control in Houston, the duty controllers continued to monitor their consoles, watching the analog clocks that counted up the elapsed time of the blackout. Gene Kranz, who had relinquished the flight director chair to Glyn Lunny for the final hours of the mission, but had remained in the control room to witness the conclusion of the rescue effort he had led, stood behind Lunny's console with his arms crossed. The time mark of 3 minutes passed. The blackout continued. The time mark of 3 minutes and 10 seconds passed, exceeding the predicted duration. The blackout continued. At 3 minutes and 30 seconds, the silence in Mission Control had become physically uncomfortable. The standard contingency consideration for an extended blackout was that the heat shield had failed. A heat shield failure would have produced no transmission at all because there would have been no command module remaining to transmit. The plasma sheath of a destroyed spacecraft did not gradually thin and disappear. It dispersed in the same instant that the spacecraft itself dispersed into incandescent debris across hundreds of miles of the Pacific Ocean. At 4 minutes, the controllers in the Mission Operations Control Room had begun to look at each other. Cy Liebergott, who had been on duty when the explosion had occurred 94 hours earlier, and who had returned to his ECOM console for the entry phase, would later say that the silence at 4 minutes was the worst sound he had ever heard. At 4 minutes and 27 seconds Greenwich Mean Time, exactly 17:58 and 12 seconds in absolute mission time, the speakers in mission control crackled with the unmistakable signature of a returning carrier signal. The aircraft search and rescue team in the South Pacific had acquired visual contact with the descending parachutes approximately 15 seconds earlier. Capsule communicator Joe Kerwin, who had transmitted the final pre-entry instructions to the crew approximately 12 minutes earlier, leaned toward his microphone and spoke the words that had been prepared for him to use during this contingency. Odyssey, Houston, standing by, over. The response, delivered in the calm cadence of a 38-year-old test pilot who had not slept more than 4 hours in any 24-hour period over the previous 4 days, came through the speakers 2 seconds later. Jack Swigert's voice. 2 words. "Okay, Joe." The Mission Operations Control Room erupted in a reaction that the controllers present that day would later struggle to describe. Some men stood and applauded. Some sat at their consoles and began to cry. Some lit cigarettes with hands that were shaking too violently to operate the lighter. Gene Kranz, standing behind Glenn Lunny's console, placed his hand on the back of Lunny's chair and leaned forward, supporting his weight on his arms. He did not speak. He did not move for nearly 30 seconds. When he straightened, his cheeks were wet. At 18:07 and 41 seconds Greenwich Mean Time on April 17, 1970, the command module Odyssey splashed down in the Pacific Ocean 4 miles from the recovery ship USS Iwo Jima. The mission elapsed time was 142 hours, 54 minutes, and 41 seconds. The 3 astronauts were recovered by helicopter and brought aboard the carrier deck within 45 minutes of splashdown. Lovell stepped onto the deck of the Iwo Jima at approximately 4 minutes past 2 p.m. Pacific time. The first thing he said, to no one in particular, was 4 words. "It's good to be back." The investigation that followed the Apollo 13 mission was the most extensive engineering review NASA had conducted to that date. The Apollo 13 Review Board, chaired by Edgar M. Cortright, the director of the Langley Research Center, began its work on April 21, 1970, 4 days after the splashdown. The board consisted of 15 members drawn from NASA, the United States Air Force, the National Academy of Sciences, and industry. It conducted 450 interviews. It reviewed approximately 96,000 pages of technical documentation. It performed extensive laboratory recreations of the failure conditions believed to have led to the explosion. The final report, delivered to the NASA administrator on June 15, 1970, ran to 1,000 pages and identified the proximate cause of the accident with a precision that the engineers who had built the oxygen tank found difficult to accept. The Cortright Commission determined that the explosion of oxygen tank number 2 had been caused by a combination of 3 independent factors, none of which would have produced a catastrophic failure on its own. The first factor was the loosened fill tube assembly, resulting from the October 1968 dropping incident at the Kennedy Space Center. The second factor was the inadequate detank procedure that had been authorized in March 1970. The third factor, and the one that the Commission identified as the single most important contributing cause, was the failure to upgrade the tank thermostats from 28-volt to 65-volt specifications, when the spacecraft electrical system had been redesigned 5 years earlier. The commission concluded that no single individual was responsible for the failure. The failure was institutional, distributed across 4 separate contractor organizations and multiple NASA engineering reviews, and reflected a systemic deficiency in the document control procedures that had governed Apollo subsystem modifications between 1965 and 1968. The engineering modifications implemented as a result of the Cortright Commission recommendations transformed every subsequent Apollo spacecraft. A third oxygen tank was added to the service module, isolated from the original 2 tanks and capable of sustaining the crew independently. The internal heaters in the cryogenic tanks were redesigned to operate within the specifications of the actual flight voltage. The Teflon insulation inside the tanks was replaced with stainless steel. Emergency battery capacity was increased. Additional water storage was provided in the command module. The procedures governing pre-flight testing of cryogenic systems were rewritten. Apollo 14, Apollo 15, Apollo 16, and Apollo 17 flew with the modified hardware. None experienced a comparable failure. The statistical record of the Apollo 13 mission, when assembled from the post-flight documentation, described an operational achievement that operated at the absolute limit of the spacecraft's design tolerances. The Lunar Module Aquarius, designed to support 2 astronauts for 45 hours of independent flight, had supported 3 astronauts for 87 hours and 56 minutes. The lithium hydroxide canisters, augmented by the mailbox adapter, had removed carbon dioxide from the cabin atmosphere for the entire duration of the lifeboat phase without exceeding the partial pressure threshold of 7.6 millimeters of mercury. The water consumption rate had been reduced from the normal 16 ounces per day per crewman to 6 ounces per day, with no crewman suffering performance-degrading dehydration during the operational phases of the mission. The total distance traveled by the spacecraft from launch to splashdown was 622,268 miles, more than any other Apollo mission. Mission control engineers working through the rescue effort had developed 47 novel procedures that had never previously existed in any Apollo flight document. Every one of those procedures had been successfully executed. The subsequent careers of the 3 astronauts diverged sharply after their return. Jim Lovell, who had been scheduled to retire from active spaceflight regardless of the Apollo 13 outcome, left NASA in March 1973. He published his memoir, Lost Moon, in 1994. The book served as the basis for the 1995 film Apollo 13, directed by Ron Howard, in which Lovell was portrayed by Tom Hanks. Lovell, who turned 98 years old in March 2026, is the last surviving member of the Apollo 13 crew. Jack Swigert remained in the astronaut corps until 1973, when he became executive director of the Committee on Science and Technology of the United States House of Representatives. He was elected to Congress from the 6th Congressional District of Colorado in November 1982. 6 weeks after his election, before he could take office, Swigert died of bone cancer at the age of 51. The diagnosis had been concealed from the voters during the final months of the campaign. Fred Haise was assigned to command Apollo 19, a mission that was canceled in September 1970, when the Apollo program was reduced from a planned 20 missions to a final total of 17. He served as a pilot for the Space Shuttle approach and landing tests in 1977, flying the prototype Shuttle Enterprise on 5 free flight test missions in the upper atmosphere over the Edwards Air Force Base. He retired from NASA in 1979 and entered private industry. He remains alive as of the time of this account, 92 years old. Gene Kranz was 67 years old when he completed the manuscript of his memoir, Failure is Not an Option, in the spring of 2000. He had retired from NASA in 1994 after a 34-year career that had encompassed every American crewed spaceflight from Mercury 7 through the early space shuttle missions. He had served as flight director for the Apollo 11 lunar landing, for the Apollo 13 rescue, and for 10 other Apollo missions. He had received the Presidential Medal of Freedom from President Richard Nixon at a ceremony in the East Room of the White House on April 18, 1970, less than 24 hours after the splashdown. In the closing pages of his memoir, Kranz offered an assessment of the Apollo 13 mission that those who knew his character recognized as the most personal evaluation he had ever placed on the public record. Apollo 13 was a failed mission. We did not reach the moon. We did not walk on Fra Mauro. We brought back no rocks. We met none of the scientific objectives that had justified the mission. By every standard normally applied to a space mission, we failed. And yet I believe, and I have believed for 30 years, that the 4 days between April 13th and April 17th, 1970, represented the finest hours of NASA and arguably the finest hours of American engineering in the 20th century. We did not save those 3 men because we were brilliant. We saved them because we had built a system, over the course of a decade, that was capable of saving them. Thousands of people were involved. Engineers who had never met the astronauts personally worked through the nights to design solutions for problems they could not have anticipated. Contractors across 48 states answered telephone calls from Houston and delivered information that became the basis for procedures that had not existed an hour earlier. The achievement was not the achievement of any individual. It was the achievement of an industrial civilization that had organized itself around a single objective for a decade, and that retained, when called upon, the capacity to improvise solutions at the limit of its technological capability. The Soviet assessment of the Apollo 13 mission, recorded in the memoirs of Boris Chertok and published in Russian between 1994 and 1999, reached a conclusion that the senior engineers of the Soviet space program had reached privately in real time as they monitored the rescue effort. We could not have done what the Americans did during those 4 days. I want to be precise about this. The deficiency was not in our engineers, who were as capable as the Americans. The deficiency was not in our cosmonauts, who would have shown the same courage. The deficiency was structural. The American system possessed depths of organizational redundancy that the Soviet system did not possess. They had multiple competing contractors developing parallel solutions. They had simulator facilities and backup crews that could be deployed within hours. They had a civilian space agency that operated with sufficient autonomy from political authority to make engineering decisions without consulting the political leadership. We had none of these things. If a Soyuz had suffered comparable damage at comparable distance from Earth, we would have lost the cosmonauts. We knew this in April 1970. The Americans demonstrated it for us, in real time, on radio frequencies we were monitoring from Moscow. The peculiar aftermath of the Apollo 13 rescue was that it did not, as many at NASA had hoped, restore American public enthusiasm for the lunar program. The television networks that had declined to broadcast the routine portions of the mission live had returned with extensive coverage of the rescue effort. Newspapers had run banner headlines. Time magazine had published a cover story. The 3 astronauts had received parades in cities across the United States. President Nixon had awarded the entire Apollo 13 flight operations team the Presidential Medal of Freedom. And then, within weeks, the American public had returned to its pre-mission disinterest. Apollo 14, launched in January 1971, drew television ratings that were lower than Apollo 12's had been before the Apollo 13 accident. Apollo 15, 16, and 17 drew progressively smaller audiences. The final Apollo mission, Apollo 17, in December 1972, drew the lowest television ratings of any Apollo flight. The men who had walked on the moon during these missions returned to an America that had largely stopped paying attention. The legacy of the Apollo 13 mission, in the more than 50 years since the splashdown of the command module Odyssey in the Pacific Ocean, has settled into a paradox that neither Gene Kranz nor Boris Chertok would have entirely predicted. The phrase, "Houston, we have a problem," slightly modified from Jack Swigert's actual transmission, has entered the global vocabulary as a universal expression of catastrophic difficulty. The mission itself is studied at the Harvard Business School, at the Stanford Graduate School of Business, at the United States Naval Academy, and at military and civilian leadership programs around the world as the definitive case study of crisis management under extreme constraints. The procedures developed during those 4 days by John Aaron, Ken Mattingly, Ed Smylie, and dozens of other engineers have been examined by aerospace agencies in Europe, Japan, China, and India. Yet the central truth that Kranz identified in his memoir has gone largely unremarked in the popular understanding of the mission. Apollo 13 was not saved by heroism. It was saved by infrastructure. The infrastructure was built over a decade by a generation of Americans whose institutional memory has largely dispersed. The men who answered the telephone calls from Houston during the night of April 13th, who walked into their offices in the early morning of April 14th to find that their employer had been temporarily redirected toward saving 3 astronauts, who applied their professional knowledge to problems they had never previously encountered, are nearly all dead now. The system they built does not exist in its original form. The capacity to improvise a rescue of comparable complexity, in the opinion of those who have studied the Apollo program in the years since, does not exist in any space agency operating in the world today. The 3 astronauts who returned from 248,000 miles in April 1970 were brought home by an America that has not entirely survived them. If this account of Apollo 13's rescue brought you closer to a moment of history that demonstrated what American industrial civilization could accomplish at its peak, consider subscribing to Space Race Tales. Every week, we bring you the untold stories of the Cold War cosmos, the cosmonauts and astronauts who flew impossible missions, the engineers who built impossible machines, and the secrets that 2 superpowers spent decades hiding from the world. The space race did not end in 1972. The stories are only beginning to be told. Subscribe, hit the notification bell, and join us for the next chapter.